operation, but what do you find out in the DC series motor? In the DC series motor, armature and field winding both are connected in series. Okay, whereas separately excited motor, the field winding gets supplied from a separate source. In case of series motor, it gets from, okay, it gets that the series field winding and the armature winding both are in series. Okay, so so then what do you find out here is that coming to the back EMF equation, okay, let me draw how it looks. It looks something like this. You have armature and the field winding. So both are connected in series. Okay. So this is field winding, this is armature. So both are in series. So you will have the supply here. So what you find out here is that whatever the current flows in the armature, same current flows in the field winding. That is the thing we must concentrate here in case of the DC series motor. Okay. So this is the case. So are the flux, the magnetic flux, okay, in case of DC series motor, okay, is coming from two parts. One part is because of the current. One part because of the current in field winding. You know? So there is a current in field winding. Generally, that current is armature current because both are in series. So one part of the flux is coming from the current in the field winding because current carrying conductor it produces a flux. This you know. So when the current flows in the field winding, that field winding will produce a flux, and that flux is this part one. Part one flux is there. Now part two flux, second part of the flux is this is because of residual flux. So I hope you might have remembered this word residual magnetism. So in the magnetic circuit, so a very magnetic circuit, it might have some residual flux or residual magnetism. Depends upon how did you operate that how did you operate previously. Say for example, previously you have used that in a particular application. Then because of that application and because of that, how much flux, uh, at what flux you have operated that magnetic circuit. So based upon these details and based upon these information, we may say that how much residual flux might be there. In case of the DC series motor, there is a residual flux is there. So this residual flux generally, why? Because you might have used this DC motor somewhere application previously. So when you have used that in previous applications, obviously as this is in series connection, definitely the armature current is same as the field current. Whereas in the previous case, if you recall the separately excited DC motor, in the separately excited DC motor, if you recall, one thing is that the field current is comparatively lesser than the armature current in some cases, or we can say this thing that, yeah, we can say this thing that, is anyone is doubt, have a doubt? Yeah, you can say this thing that the field winding, its excitation is remains constant in case of separately excited, whereas in this case it continuously varies. So and one more thing is that current depends upon the speed of the motor here. Why it depends upon the speed of the motor? Because it depends upon the speed of, there is an equation is there. I will write this side here. EP back EMF is equal to 5 ZN by 16 to P by A. This is the equation, general equation for all the DC motors. Okay. Now you see here now, this phi is there. Okay. This phi is constant in case of separately excited motor. Whereas in case of DC series motor, this is not constant. Okay. because it depends upon the armature current that is connected in series with the armature. And second thing is that the speed is there. So in another words, we can say this thing that this flux phi, okay, this flux phi, it depends upon IA value. So when it depends upon IA value, and there is another equation between IA and so VA is equal to EB plus IA RA. This is one equation. So EB and IA has some relationship. Similarly, EB and phi has some other relationship. Okay, because of this relationship, when EB changes, IA also changes. When IA changes, your flux also changes. So your flux is variable here in case of the DC series motor generally. So that's the reason that sometimes it is difficult for controlling the speed of the DC series motor comparatively with the separately excited DC motor. So because of all these several reasons, there is some residual magnetism, which is a considerable amount. Considerable amount in the sense you cannot neglect that amount generally. So that much amount of the flux is present in case of the DC series motor, and that you call it as a residual flux. So generally you can represent that as some RES by RES. So part 1 flux which is depends upon IA, whereas part 2 flux that is residual flux generally it depends upon the speed. Generally it depends on speed. Okay. But in our case we will consider this as constant. Constant in the sense with respect to load current or with respect to the armature current, this is constant. So it does not depend upon the armature current. It's simply constant. It mainly depends upon the speed. So when you have used the series motor somewhere else with some speed, so at that time, based upon that speed, your residual magnetism may be decided. Now, once you are using in some other application, this residual magnetism generally you treat this as constant. You treat this as constant. Okay. So so now you see here. Okay, this is the thing which you know already. I'm just revising this. You must have gone across this. Okay, about the DC series motor and separate Lexer motor, how it is different in case of the operation. Okay, because as the field winding is in series with the armature, then some of the features which you find out in the separate Lexer motor will not be found here. Especially, you generally don't use the series motor whenever the application requires a continuous speed change. Whenever the application requires a continuous speed change, generally you don't go for a series motor. You generally go for the separate external DC motor because of the reasons. One reason is that the field winding is in series with the armature. Okay, and because of that, some other equations will change and some other properties also will change. Okay? This is briefly about series DC series motor, which you must know. And so the back EMF. Now the back EMF generally, okay. Now you see here, your back EMF depends upon what? The back EMF depends upon, okay, the flux. The back EMF depends upon the flux here. You see now, the back EMF it depends upon the flux. So or it is a function of flux. We can say like this. But what you have found in the DC motor, it is having two parts of the flux. So one part of the flux is because of the current, okay, in the field winding, and that current is generally armature current because both are in series. And another one is residual flux. So I can say this thing that back EMF also two parts, EB1 and EB2. Of course, both are, you have to add both. So EB1 is because of the first one, that is because of the flux in the field winding, and that is because of the armature current. So I will write this thing as what I will write this thing as some constant K1 into IA into N, because N is there here also, even in the back EMF. So only thing is that what is the nature of this phi? It depends upon that nature. We are doing something here. What is that nature? Now phi is a variable or phi is a constant. Now in this DC series motor, you have two fluxes. One flux is variable and it depends upon IA. Another flux is constant. So first flux is a variable which depends upon IA. So what I did is that I represented this phi, first phi, that is the variable phi, in terms of IA, and N is always there. So N I put. Now second one K2 I put constant K2. Now second one is because of the residual flux, and I said this is a constant. It does not depend upon the armature current. So this value is constant. So your flux phi is constant in this case. In the second case. What about N? N is there always. So N you represent like this. So then what is the total what is the total what is the total flux now? What is the total EMF now in this case? If you think, then I can say this thing that K1 IAN plus K2N. So this is the back EMF equation in case of the DC series motor. So this is different from the previous case. You must understand why it is different from the previous case is that there we did not consider about the residual magnetism because of the nature of the motor. Now, as this is a DC series motor, you got two types of EMFs. One EMF is because of each EMF is because of each flux. Both are different here. Okay. And what about the torque now? What about the torque? So what you must understand here is that one important thing is that so as we have two back EMFs once again. So what about the torque equation? If you recall, torque equation is generally EB into IA. This you know very well. Okay. So when you compare, what you must understand here is that whether you will consider here, whether you don't consider, it depends upon. If you consider, the system becomes a little bit complex and the analysis also becomes a little bit complex. But if you neglect when it comes to the case of the torque, so torque is also because of two EMFs, one EMF. So now what you will know later is that the torque because of this residual flux, the torque because of this residual flux, okay, is very small compared with this torque. So to make this analysis simple, generally what you do is that you will neglect this part. When it comes to the case of torque, when it comes to the case of the torque, you generally neglect this part. So this flux, you residual flux, you generally neglect. So the torque you generally consider only because of the first part. So when you consider only because of the first part, you will write K1. Okay. So you write K1 here. So K1. I'm sorry that there is omega is there here. So something I will write here. K1 K1 IAN by omega into this is EB, yeah, into IA. So this is the equation you will find out. EB into IA by omega. So this is a torque expression. Okay. So then so you can write like this. So this n is there here. Here you will get one more n here because it is 2 pi n by 60. So 2 pi by 60 is constant. So n will get cancelled. So this constant will be modified to another constant. So I will write something like this, some KT IA square. That's it. So your torque is KT into IA square. So this I'm sure that this you know already that in case of the DC series motor, the torque is proportional to IA square in case of the DC series motor. Okay. So and that already we have drawn that. Okay. So now this analysis we require to go ahead with some more things. To go ahead with some more things. Okay. So now we'll go ahead with this. Once you know a little bit about this DC series motor, then we will extend our topic to uh, single phase semi controlled converter fed single phase semi controlled converter fed DC series motor. Now we will do this analysis like we did this analysis even for the case of your separated DC motor. Here also we do the same thing. Now. So what is the circuit diagram you will get here is that I hope you remember semi control converter. So, so what you will find out here? Now you connect the motor here. So, so two resistors, two diodes. Okay. RA plus RF. LF. So why I put RA plus RF is that one is because of the armature, one resistance, other is because of the field resistance. So you have two resistance here. Now whether you have two or three resistance, but they are something like this in series with this. Okay. Then what we will do now? We forgot one more thing that there is a freewheeling diode is here. Yeah. This is EB. Okay. So yes. Okay. So so now, if you recall previously the operation of the semi-controlled converter, you might have known this thing that you have two types of conduction modes. Okay, continuous conduction mode and discontinuous conduction mode. Okay, so the same procedure here also will follow continuous conduction and discontinuous conduction. First, we go for the continuous conduction. So I hope you remember this thing. What is the continuous conduction and what it is? So, because in continuous conduction, yeah, in continuous conduction, what you will find out is that the current will never be zero. The current will never be zero throughout the cycle. So it is Vs, it is omega. It is phi, it is 2 pi. Okay. So this one. So this is supply voltage. Here the supply voltage is there. Then we'll find out the output voltage Va. We find out the voltage Va here. So here you will get omega is pi is here, 2 pi is here. Okay. 2 pi is here, 2 pi is here. Okay. So so what you find out here is that the continuous conduction. Now you know very well that you need a firing angle alpha, here pi plus alpha. So at alpha, you trigger thyristor number one. So when you trigger thyristor number one, automatically DT will be forward biased. Okay. So D2 will be forward biased. Okay, D2 will be forward biased. Diode D2 and thyristor 1 will conduct. So through the load it will conduct. So when these two are conducting, you have seen already that the output voltage VA is same as the supply voltage. Okay, so we'll find out something like this. Okay. So so now the question is that after pi what will happen? After pi the supply voltage becomes negative. So when the supply voltage becomes negative, you will find out that What do you find out is that the current which is there in the inductor from alpha to pi, I will write here omega t alpha less than equal to omega t less than equal to pi. So during this portion, output voltage is same as supply voltage. So I have drawn that then after pi, the supply voltage becomes negative. So the current in the inductor will take a path through the freewheeling diode. So it will take a path through the freewheeling diode. Okay. So it will take through the freewheeling diode. Okay. So it takes to the freewheeling diode. That is from pi to pi plus alpha. Why pi to pi plus alpha? Because pi plus alpha once again you trigger thyristor 2. When you trigger thyristor 2, so then what you find out is that the voltage, this freewheeling diode will become reverse bias. So you will find out this thing that okay. So the black is one type of conduction, the blue is another type of conduction. So in that case, I will write here. So when it is triggering, you see here when the freewheeling diode is conducting, you know the voltage is zero. The voltage is zero. Correctly, the voltage is zero. Now at pi plus alpha, once again you trigger, then what do you find out is that. So let me complete this waveform also. Here also it is zero. Yeah, this is the output voltage. I now what is the output current IA? IA will be something like this. So what is IA value? So simple thing that IA is nothing but the current in the current. So in IA in the sense is nothing but okay RL circuit. So RL circuit in the sense sinusoidal voltage you are giving. So something will as it is a continuous conduction you will find out something like this. The waveform I told you already. So you'll find out a continuous conduction. So the current in the inductor is never become zero. So it is always a non-zero value. Okay, this is the continuous conduction. So I will write here between pi to pi plus alpha. In this case, it is VA is equal to VS. In this case, VA is equal to zero because freewheeling diode is conducting. Then what is the average value? If you find out the average value of the output voltage, what do you find out VA average? So 1 by time period, so 1 by pi integral alpha to pi. Why I am saying because pi to pi plus alpha it is zero. So I will remove that omega t d of omega t. Okay, then 1 by that is Vm by pi minus cos omega t alpha to pi. Okay. So what you find out here is the answer is that Vm by pi into 1 plus cos alpha. This is the expression for the average voltage. Expression for the average voltage. Okay. Now once you got this expression, now you recall what is the equation for VA? Generally, VA is equal to EB plus IA RA. This you know. So that implies VA value is Vm by pi into 1 plus cos alpha. That is equal. EB in the sense I told you already, the EB equation is different here. So because it has two parts are there. So let's see both of these equations. K1 IAN plus K2 N. So this is EB plus IA RA. IA. So this is the expression you got. Then from this, I want to know what is N. I want to know what is N. Then if I can draw what is N, then divided by K1 IA plus K2. This you will find out. This you will find out. Okay. So once you got this, then we have another equation for torque and current. What is that equation we got here just now? T is equal KT into IA square. So T is equal KT into IA square. Then what is IA from this? IA is equal T by KT over square root. This is it. Now substitute this IA here. So if you substitute this IA here, then what you find out is that M is equal to Vm by 5 into 1 plus cos alpha minus root T by KT into RA whole divided by K1 root T by KT K2. So now in this equation you find out there is N is there, there is T is there, here is T is there, here is there. Remaining all are constants, or we can say remaining all depends upon the value of alpha. Except alpha, remaining all are constants. So this is the relationship between speed and torque in this case. This is what you must understand, that what is the relationship between speed and torque. Okay, this way you can get the relationship. Okay, so now what else is there in this is that, so if I can draw the speed torque characteristics, okay, then I will draw speed torque characteristics because we know the relationship between speed and torque. Speed torque characteristics. So this is the speed and this is the torque. Okay, this is the torque. So now you start with t is equal to 0. Say for example, if I take t is equal to 0, this part is 0, this part is 0, then k2 is left. Then it depends upon the value of alpha. So if alpha is minimum, then that speed is maximum. So just substituting the value, then we will find out here. Is one point. For this point is for alpha is equal to 0. Then if I go on increase t value, then what you find out is that if I go on increase the t value, then the numerator decreases whereas denominator increases. Now you see yourself. Numerator decreases, the total numerator decreases, but the denominator increases. So it means the total thing is that the decrement will be further. So the decrement is not a linear one, it's a non-linear decrement. So it decreases much. Something like this we'll find out. Okay. See, remember, it's this is not is a non-linear equation, non-linear graph here. Similarly, you increase alpha value, then you will find out this value decreases. So then some 30 is there, or upper some 60 is there, or 40. So you go on increase that, then you will get this graph. Okay. So this is the case of continuous conduction. Okay, now when I go for the discontinuous conduction, what do you find out in case of discontinuous conduction? Okay, so let me take this picture here. Yeah. In case of discontinuous conduction, now let me go for the discontinuous conduction. Now this is for discontinuous conduction. So So I hope you know what is discontinuous conduction. So discontinuous conduction in the sense. So if you recall the discontinuous conduction, so what do you find out in the discontinuous conduction is that, see, a part of the energy which was circulating earlier in this, okay, so will not be there. So first case is that from alpha to pi if you take, from alpha to pi if you take, so then what do you find out from alpha to pi is that, okay, let me take alpha is equal to omega t less than equal to pi. So in this case, your VA is equal to VS. Okay. Because resistance 1 and diode 2 will conduct. So, so we'll write here. Yeah. At pi, what do you find out is that at pi, freewheeling diode will conduct. So the freewheeling diode will conduct because the supply voltage is negative. So the energy in the inductor will circulate through the freewheeling diode. So before pi plus alpha, let me take some value beta. Now beta. So till beta, I will let the beta here. So till beta, the energy in the armature of your motor, that is in the inductance of this armature. So till beta, that energy will go. That energy will be over. So when the energy is over now, no energy is left in the inductor. So when no energy is left in the inductor, you will find out that the armature current IA will become zero. So when the armature current IA becomes zero, then if you apply KVL just like how we did in case of the discontinuous conduction, even in case of the separate accelerator motor, the output voltage is same as, so I will write here phi beta, in this case VA is equal to 0. Whereas the next duration beta less than equal to omega t less than equal to pi plus alpha, in this case IA is 0, IA is 0. So when IA is 0, VA is equal to EB. Why EB is that? Because because the back EMF is present. Why the back EMF is present? Because it is still running. When it is still running, so you still have the back EMF. Okay. So yeah, then what do you find out here is that small back EMF will be there, and that back EMF will continue. Maybe it is not. You can consider this as a constant this time, because in case of the previous analysis, what you find out is that I have drawn this as a decreasing one, whereas now this case I have drawn this as a constant one. So the reason behind is that I told you already that there is a residual magnetism is there. So because of that residual magnetism, okay, because of that residual magnetism, so the back EMF is present, and that back EMF is proportional to speed. Okay, and of course the speed is decreasing here, or you may take it as constant here. If you think that that decrement will be, what I'm saying is that residual flux is more or less it's constant. So when it is constant, when that residual flux is constant, okay, so then what do you find out here is that the back EMF is more or less constant. So it only depends upon the speed, and that speed, okay, here you consider either it's a constant or it's a variable. Okay, so that really does not much will be there, much difference will not be there. Even you can take it as here decrement also, no problem. Okay, so but in case of the series motor, what do you find out is that this decrement will not be much, because the flux here, who is here the flux who is here operating here is that the residual flux. Okay, so then after that the cycle repeats the same time. Okay, so here also we'll continue this here. So this is the output voltage in case of discontinuous conduction. Whereas, what about the current waveform now? I told you the current okay will be 0 in third interval. So that is from beta to pi plus alpha. So right here, so here 0, then once again it will increase. Sorry, 0 here once again it will increase. It will extend till beta. From beta to alpha it is 0. Then once again it will extend like this. So likewise it will go ahead. So now you see there is a discontinuity is there here in this case. So this IA is there. Okay. So this is the discontinuous conductance. The analysis is same. There is not much difference here. Okay. So then what do you find out here is that, so in that case, what is the output voltage VA? Okay. So the output voltage of VA, you just recall in case of separated resistor DC motor, in case of that, whatever the VA you got, you will get the same VA here because the waveform does not change, because VA depends upon the waveform. So the intervals, VA depends upon the waveform and interval. Now you see the same intervals and the same waveform you will find out even in case of the separated DC motor. There also we consider EV is constant when we do the derivation. So here also same thing. So that derivation I'm not going to do that. Okay. So that value, okay, that value, whatever you got in case of the discontinuous conduction mode, you will get the same thing here also. And one more thing, what is the expression for IA? The expression for IA also same thing, that whatever you got in case of your separate electric motor, here also you will get, except where do you find out RA? In place of RA, you find out RA plus RA. Nothing else is there. And remaining everything is same. If you look at the waveforms, or if you look at these circuit diagrams, or if you look at the intervals. So for the discontinuous conduction mode, VA expression and IA expression, you will get same, except wherever you find out RA. In that case, you replace RA with RA plus RA, and nothing else is there because the circuit does not change.